Hello, hope you guys can hear me. I'm going to be learning C++ this stream again, and I noticed that last stream my audio was kind of choppy. I hope that doesn't happen this stream. And I want to revise chapter 7. I'm thinking of redoing chapter 7 again, and I might delete my last stream. So if anyone is watching this in the future, my last stream is I'm redoing my last stream, and the first version is basically deleted, or at least I'm intending to delete it. Uh, Wait, hold on. Let me just change to full screen. Okay. So this is all the PDF from learncpp.com. I did chapter 7. Wait, hold on. Okay. I did chapter 7 last stream, but I'm going to revise it this stream because, well, I'm going to relearn it. Okay. And yeah, so chapter 7.1 compound statements. Okay. A compound statement, also called a block or block statement, is a group of 0 or more statements that is treated by the compiler as if it were a single statement. Also, it's grouped within curly brackets. I might rush through some of these segments because I'm relearning it. You may have already seen an example. So int add, return, and int main. Blocks inside other blocks. Although functions can't be nested inside other functions, blocks can be nested inside other blocks. So int add, multiple statements. Okay, wait. Let's see. So we have int xy. So add is, I think I would remove the comments. Then you have a block here. And then later what they're going to mention. Is there any variable inside here? So like int x is defined here. It's defined within this block, but it gets deleted as soon as it goes out of the blocks. So x gets deleted outside block. But I think they will mention that later. Local variables. Using blocks to execute multiple statements conditionally. So we went through if and else, but we did like single statements. So add. So let's say a value if value is more than 7. Is there a shortcut to delete just the comments? Std cout value and then let's say for example I increment this value. So basically what I'm doing is that I have multiple statements. I can group them all together. So before it was like this, where you do if and then the statement runs. But we can only do this with one statement. But now if we add curly brackets, we can have multiple statements. Same thing with else. Okay. Block nesting level. So the outermost block is nesting level 1. And then the one after that is nesting level 2. And then the one after that is 3, 4, and so on. Also, the values in the upper nesting value can be accessed by the ones in the lower level. So I think the value is defined here. It can be accessed within this block. And then so if I do this, let's do this, and then I run it. What I'm trying to show is that value can be accessed from inside the lower nesting level and on the same level as well. But integers in the lower nesting level, like if they're initialized in the lower nesting level, they can't be accessed by the outer level. Uh, and I just complete this. Okay, so 7, 8, 8. So 7 from here, 8 from here, and then 8 from here. But if I do int x, which is, I guess, default initialization, then I do x here, this should give an error. The ones in the lower nesting level can't be accessed in the outer level. They get deleted once you go out of their scope. So this should give an error. Yeah, failed. So there's a C. C means compiler error. X, undeclared identifier. So X is not recognized. Also, it's not syntax highlighted either. You keep the next nesting level of your functions to 3 or less. Oh, if it's too deep, then you would separate them into other functions. User-defined namespaces and the scope resolution operator. So user-defined namespaces is like this std over here. So in IOStream, if I go to this function, for name conflict issues, like to prevent naming conflicts. Okay, I don't know where the namespace stuff is. How do I get there? Yeah, I don't know how to. I'm still new to C++, so basically we can define our own namespace, which I think is like this if I remember correctly. Namespace, custom namespace. Is it like this? Yeah. And then I can define my own values like int uh, common variable 5. And then this variable, if I want to access it, I have to do like this. Custom namespace. I do colon colon and then common variable. The purpose for this is if you have like lots of files and then there's a common name, you want to prevent naming conflicts. There's a common name or common function in those multiple files. Then you use uh, namespace namespaces to differentiate between them, to like group them. So namespace 1, namespace 2, I do namespace 1. So basically I have multiple CSS files. So this common variable is in a separate file. This common variable is also in a separate file, but in order to differentiate them, I can group them into namespaces. So common variable of this one is in namespace 1, and this common variable is in namespace 2. And if I want to call them, I can call them like this. So this way I can have the same name, common variable, by putting them in separate groups. And that's basically the gist of it. Also, putting variables in a global scope is a bad idea. They don't recommend this. Putting non-constant global scope variables is a bad idea, but they will go through that later. Anyways, uh, the scope resolution operator, or those two columns, those are uh, scope resolution operators. Okay. So foo.cpp, over here they have foo.cpp, which has the function do something. They have goo.cpp, which has the function do something. And main.cpp is declaring the do something, forward declaring for do something. But the linker, I think, is confused. By compiling both into the same program, we have now introduced two different functions with the same name and parameters into the same scope, the global scope, which causes a naming resolution. Oh, it's a linker error. Yeah. Wait, so what they're saying is int do something return return 5. Let's say I add a header file. Add new item. Header file. Add. Okay, forget this. Foo.h. And then I define do something over here. Then I have goo.h. Cannot copy Visual C++ within the same project when show all files is turned off. How do I turn on? Go. So this, and then this one would return 6. Now let's include them. Foo.h, go.h, and then let's try to. There should be a naming conflict. Wait, hold on. Now let's run again. There should be a linker error because it's including do something twice, and it's getting confused, and it won't notice the two definitions. See previous definition of do something. Function int do something void already has a body. So this error is from go.h, but I can resolve this. So let's say I want to do stdc out. Do something. But I can resolve this using namespaces. Namespace go. Namespace. This one will be foo. Who added this comment? And now I can do go and then foo. And then now it can differentiate between the two. I think namespace has its own scope. So functions on the outer level are at a global scope. But when you introduce namespace, now this has its own scope, the foo scope. Yeah, they're talking about namespaces. The convention is to name program defined types starting with a capital letter. Using the same convention for program defined namespaces is consistent. especially when using a qualified name such as capital FOO, where FO capital FO could be a namespace or a class type. What's the issue? X local variable is initialized but not referenced. Oh, I have warnings. Treat warnings as errors on. A namespace must be defined either in the global scope or inside another namespace. Oh, wait, you can use an alias as well, right? For namespaces. Hold on, let me see where that was. Okay, I'll get back to that. And then they say, wait, where is it? Using scope resolution operator with no name prefix. Want to revise that. Yeah, 7866. Why does it? Oh, for both of them I did 6. That's okay. Also, they introduced a no name prefix. Wait, wait. Since I have names scope, I can do. It's better, I think. I do return 5, and I can also do int do something return 7. Now let's try. Wait, no, hold on. This will refer to the global scope. How do I cancel this build? It's not responding. Six five. Okay, that works. And this would be the global scope. What's the point of the no name prefix? I forgot. Call print in global namespace, same as calling print in this case. Like calling print without the scope resolution operator. Identify resolution from within a namespace. Wait, let me just wait for this to complete. An identifier inside a namespace is used and no scope resolution is provided. The compiler will first try to find a matching declaration in that same namespace. So let me see. So namespace foo print. If you do print, oh, I see. So this with the colon, it's in the global namespace, but without the global names, without the colon, it finds the closest namespace. Yeah, I think I understand. 657. 657. Okay, that's correct. So anyways, what they were saying is that if I have namespace 1 and then namespace 2, and then this is defined in namespace 1, print something, return, do something, plus it with, do something. Why isn't this recognized? Okay, I think what is supposed to happen is that this do something is in the namespace of foo2. But if foo2 isn't here, then it's in the namespace of foo1. It's in the like previous namespace, the closest namespace. Why is it doing this? Definition do something could not be located, but it's right here. Oh, wait. Hold on. Yeah. This do something. It finds the definition. It goes up. It finds the definition for do something in its own namespace. If it's not here, it goes to the previous namespace. If it's not here, it goes to the previous namespace up until the global namespace. So this is like uh, without any scope resolution operator, it's like the closest namespace where do something's defined. And this would definitely give the global namespace. So this should give 5 plus 7. Let's do 4 1 and then 4 2. And print something. Print something. Yeah. It says failed. Compiler do something is not a member of global namespace. Okay. Looks like this is an issue. Because do something is defined here, right? But include foo happens later. What happens if I do this? I think this is really bad practice, but let's see. Or 9 compiles. 6, which is good or do something. 7, which is do something in the global level. And then foo1, foo2, print something, which is 5 plus 7. This is correct. Okay, let's see. So over here, if I dot h namespace basic math dot cpp, or they've just declared it, but they did not define it. Multiple namespace blocks are allowed. Okay, basic math, basic math. This is what I was looking for. So foo and go can do it twice, but there's a way to use an alias so you don't have to type so much in case if there are multiple. Yeah, namespace. Okay, hold on. I think I should have another header. Global stuff. Why? How do I remove this pragma once that keeps happening? Let's see. Namespace inner foo, and then I can do foo1, foo2, right? Yeah, and then this would work. This would do the same thing. We can avoid writing long namespaces like that. In multi-team organizations, 2-level or even 3-level namespaces are often used to prevent conflicts between code generated by different teams. These often take the form of one of the following: so project or library, module, so foo logger lang, company or organization, project or library, or company or organization, project, library, and then module. Right. Local variables. Oh, I said last time that x define inside. Wait, hold on. If I have an inner block, let's just do if value is more than 7, and then int value let's just do 8. If I do int x value x has 5, and then x here as well. So basically what I was saying last time, because n is defined here within this block, it will get deleted as soon as the program exits this block. This is called block scope. Although function parameters are not defined inside the function body, they're considered part of the scope of the function body, or even the parameters here. Yeah, their scope is inside the function. Let's do this. Is there a way to remove all the comments? All variables named within a scope must be unique. Also, another thing, they will introduce the, like later on they will introduce variable shadowing. So if I do int value 9, whoops, 9, this value over here is a separate thing from this. So if I'm printing value, it's referring to the one defined within this scope and not this. So wait, let me remove this because it will cause an error. Let me run this. So it should be 8 and then 9 referring to the inner value, and then the inner value gets deleted, so this will refer to 8 again. I think this is called variable shadowing, I think, with the because this gets hidden now that I define this. Let's see. See declaration. Oh, this is a warning. I have warning being treated as errors turned on. So the following warning is treated as an error. Declaration of value hides previous local declaration. Okay, so they won't allow this. But if warning is as error is turned off, then this would have printed 9. Local variables have automatic storage duration, which means they are created at the point of definition. So I is created here, D is created here, and then they're both destroyed here. And destroyed at the end of the block they define it. Okay, so this type of duration is called automatic storage duration. An identifier's linkage determines whether a declaration of that same identifier in a different scope refers to the same object or function. Okay, the linkage part confuses me, but they will go through it again later on. A linkage determines whether a declaration, okay, of that same identifier in a different scope refers to the same object. So value here is different from the value here. So there's no linkage. Variables should be defined in the most limited scope. Or this, what they're meaning is, if I'm only using y over here, if there's no std out over here, if I'm only using y over here, then I should define y within this scope. There's no point for my memory to be holding y in the above scope. Introduction to global variables. Okay, so within these blocks, they're local variables. But if I have this value over here, now it's a global variable. And of course, if some library is using this, they would be able to use the global variable. Wait, let's do this. Global stuff.h. Let's define all the global variables here. Int value 9. So this should print 9, right? Or would it give a warning? Yeah, 5, 9. Global variable. Also, they said it's a good practice to have like a g underscore for variables like this. So global value, and then it should be global value, global value. The scope, global namespace scope, which means they are visible from the point of declaration until the end of the file in which they declared. I think it's until the end of the main function actually. Okay, so consider using g or underscore g prefix. Yeah, 0 initialized by default, constant. Just like local variables, global variables can be constant. As without constant, constant global variables must be initialized. Okay. Also, they said non-constant global variables are bad, but they will go more in depth later on. And this is variable sharding, what I was talking about. So this apples, so apple over here, apples over here refers to like 10 is assigned to apples, but this apples over here refers to this and not this. Is there anything? Sharding of global variables. Avoid sharding. Oh, yeah, I did get a warning about it. Now linkage. Linkage is the confusing bit for me. Internal linkage and identifier with internal linkage can be seen and used within a single translation unit. So when they say translation unit, I think they're referring to one file. I think when the preprocessor is finished, or after the preprocessor is finished, you end up with a translation unit. And so it's referring to one specific file. The files are not combined together until you come across the linker. That's the linker's job. So it's like, I think preprocessor and then compilation. Preprocessor is part of the compilation, and then linker, and then the linking happened here. This is how the process goes. I think as a result of the preprocessor, you get a translation unit, and then this gives object files, and then this gives exe. This links all the object files, and then you get an exe. Now, what was I thinking? Yeah, if I have a global variable, like let's say int, if I have this global variable, if I do static, only this file can see this global variable. G value, I don't think it can be seen here. Or can it? Let's see. No, I think once the preprocessor is finished, it unpacks global stuff.h, right? So I think this file, this main.cpp, would be able to see global, this value. Yeah. Internal linkage. That means if two source files have identically named identifiers with internal linkage, those identifiers will be treated as independent. So you use the static keyword to make them internal. And then const by default are internal linkage. So you don't need static for const. So static ngx, because gx is internal to each file, main.cpp has no idea that a.cpp has variable named gx. But you're not including it, right? Hold on, did I just skip through? Why bother giving identifiers internal linkage? There are typically two types of reason to give identifiers internal linkage. There is an identifier we want to make sure isn't accessible to other files. This could be a global variable we don't want to mess with. And to be pedantic about avoiding naming collisions, because identifiers with internal linkage aren't exposed to the linker. But there's something I don't understand. Once the preprocessor is done, wouldn't it open all of this up? So wouldn't everything be in a single translation unit? You can do static with functions as well. Okay, that's one question I have. Uh, Hold on. External linkage and variable forward declarations. Functions have external linkage by default. So a.cpp, or say hi, main.cpp, say hi. Wait, if I do another cpp file and I don't include it, what would happen? Let's see. Say hi. Main.cpp, and then I guess say hi. Why is there no syntax highlighting? Don't I need to include? Wait, let me declare it. Void say hi. Hi. And then void say hi is here. And then I think the Visual Studio will automatically link those two. Let's see what it says. Okay, yeah. So I can show static over here. So if I forget, let's just forget this. Okay, static is shown to main.cpp, but a.cpp doesn't see static. So if I do uh, g underscore value thing, it won't see it, right? Yeah. And then if I do static, this is available in one translation unit, so only a.cpp sees it. Main.cpp doesn't see it, right? Let's see. I think it should cause a linker error because say hi was never defined even after linking. Okay, so it's compiling a.cpp. Main.cpp is going to cause an error. The following warning is treated as an error. Unreferenced function with internal linkage has been removed. Okay, so it failed. So this function is defined in a.cpp, but main can't access it. Only so this will be one translation unit. This along with these three headers would be one translation unit. So internal linkage means only like this function can only be accessed within their own translation unit. Okay, functions by default have external linkage. So if I have const g underscore by 3.14, right? And let's say, let's do this. And then this. And then this. So g value by default they have non-constants by default have external linkage and constant by default have internal linkage, I think. So global stuff and a.cpp are together in one translation unit And then foo, go, and main.cpp are in one translation unit. Let's remove this. Yeah, G value is not recognized until I do extern, till I make it external. Now I think it would be recognized. They have to do extern here as well. Extern G underscore value. Let's see. Now they both are referring to the same G value. Think constants by default. I think I was wrong last time. Constants by default have external linkage. Let me check again. Global variables with external linkage. Okay. Non-constants are external by default. Constants are internal by default. So we have to make them external. Okay, I get it. Hold on. I did not specify the type. Float. Let's see. Is it like this? I think. So extern float int G value, and then int G value and initialized it, and then std cout G underscore pi. But wait, I can't declare it, right? I need a value. So how would I do that? Also, it shouldn't be equal. It should be, I keep forgetting. I can do forward declaration with global. Okay, I think normally they don't recommend it, but I think this case is in with external. It's an exception. External G underscore pi. Now let's see. So it's compiling a.cpp. And then main.cpp. And then missing type specifier because I forgot to mention that this is a float. Let's see. Main.cpp. One or more multiply defined symbols found. Int underscore G value already defined in a.object. G value. So I can remove this. But I need to declare it, right? Otherwise, how would they know? Oh, we need to provide the extern keyword. External link. Then wait. I think we only need the extern keyword during the. Hold on. Forget what I said. So int is external by default. Const is static by default, but we are making it external. And then we are declaring these two. But since we have external keyword on both of them, that means their definition is somewhere else. This should work. Okay, let's see. 5.9 high 3.14. So 5.9 high 3.14. Okay. So we do need extern here, right? Otherwise the program will assume that this is static. Let's see what they're doing. Okay, they are defining extern. If you want to define an uninitialized non-constant global variable, do not use extern keyword, otherwise C++ will think you're trying to make a forward declaration. Okay. So this is assumed that it's external, but if I do type external explicitly here, that means the definition is somewhere else. Also, they cannot be forward declared as God's expression. Okay. So the matching of the values happens at the linking stage. Okay, so the value cannot be evaluatable at compile time. So they cannot be const expression. Avoid using extern on a non-constant global variable with an initializer. Uh, the following two lines are semantically equivalent. However, your compiler may issue a warning about lattice statement, even though it is technically valid. Okay. Okay, now they're talking about why non-constant global variables are evil. If you were to ask a veteran programmer for one piece of advice on good programming practices, after some thought, the most likely answer would be avoid global variables. I think they're referring to non-constant maybe. By far, the biggest reason non-constant global variables are dangerous is because their values can be changed by any function that is called. And there's no easy way for programming to know that this will happen. Wait, let's test this out. So we have g value. Let's just change the value of the global variable. G value is 10. It actually changed. So anyone can change the global value. That's why they're bad. with global values, with global variables, it's not uncommon to find a piece of code that looks like this. Some useful code, gmod for do something. After debugging, you determine that your program isn't working correctly because gmod has value 3 and not 4. How do you fix it? Oh, I see. So debugging is more difficult because gmod can be changed literally anywhere. So that's why local is better. Um, Initialization of static variables, which include global variables, happens as part of program startup before execution of the main function. This proceeds in two phases. First phase is called static initialization, uh, where global variables with constant expression initializer are initialized to those values. This is called constant initialization. Global variables without initializer are zero initialized. And then the second phase is dynamic initialization. Phase is more complex and nuanced, but the gist of it is that global variables with non-constant expressions are initialized. Here's an example of non-constant expression initializer. Okay, so this over here. So this happens during the second phase. Wait, hold on. This is assumed external, right? Static initialization. Okay, yeah. But this is not static initialization. This is dynamic initialization. Yeah, yeah. No, but they're talking about initialization of static variables. This is not static, this is external. Within a single file for each phase, global variables are generally initialized in order of definition. Given this, you need to be careful not to have variables dependent on the initialization value of other variables that won't be initialized until later. Oh, this is causing a loop. So gx is initiate x, but initiate x is using gy, and then gy is using initiate y. And gy is likely defined later. So this prints 0 and 5 when the user wanted 5 and 5. So what are very good reasons to use non-constant global variables? There aren't many. In most cases, using local variables and passing them as arguments to other functions is preferable. A good example is log file where you dump error and debug information. It probably makes sense to define this as a global because you're likely to have one such log in a program and it will likely be used everywhere in your program. Another example would be a random number generator. Okay, so 7.9 inline function. Oh, the inline part confused me last time. Um, it, Consider the following example. So we int minimum. Okay, we have that here. We have max twice. So let's do std cout max 4 and 5, and then new line, and then 14 and 50. And then remove all this. And remove these two as well. So what are they saying? Okay, wait. I can just put this over here. Right. So returning the max value. Whenever a call to, in my case, max is encountered, the CPU must store the address of the current instruction it is executing so it knows where to return later, along with the values of various CPU registers. Then parameters x and y must be instantiated, then initialized. Okay. Think so when it calls this, these two must be initialized. And then this must be, what do you call it? Okay. So it needs to store this instruction somewhere so I can return back to it later. And then it goes to max and then it does the max stuff. All of the extra work, wait. And then the execution path has to jump to the code in the max function. When the function ends, the program has to jump back to the location of the function call. Okay, so do all the max stuff and then jump back over here. Jump back to main. All of the extra work must happen to set up, facilitate, and or clean up after some task. And all of this is called overhead. For functions that are large and perform complex tasks, the overhead of the function call is typically insignificant compared to the amount of time the function takes to run. However, for small functions such as minimum, in my case maximum, the overhead cost can be larger than the time needed to actually execute the function's code. In such cases where a small function is called often, using a function can result in significant performance penalty overwriting the same code in place. Fortunately, the C++ compiler has a trick that it can use to avoid such overhead cost. Inline expansion is a process where a function call is replaced by the code from the called function. For example, if the compiler expanded the, in my case, max calls in the above examples, the resulting code would look like this. Basically, max is replaced with this code. So you don't need to like do the CPU overhead thing. The performance of inline code, beyond removing the cost of function called inline expansion, can also allow the compiler to optimize the resulting code more efficiently. However, inline expansion has its own potential costs. If the body of the function being expanded takes more instructions than the function call being replaced, then each inline expansion will cause executable to grow larger. Large executables tend to be slower due to not fitting as well in memory caches. So we have to choose whether we want to do it inline or in a separate function. But I think for small functions, we should just do it inline. The inline keyword historically. Historically, compilers don't have the capability to determine whether inline expansion would be beneficial or were not very good at it. For this reason, C++ provided the keyword inline, which was originally intended to be used as a hint to the compiler that a function would probably benefit from being expanded inline. So here's an example. Okay, so I think if I do inline over here, then during the compilation, this will replace this. So you don't need the function overhead. Form of premature optimization. Do not use inline keyword to request inline expansion for your functions. Modern optimizing compilers are typically good at determining which function calls should be made inline, better than humans in most cases. Okay, so let's jump to modern times. In modern C++, the term inline has evolved to mean multiple definitions allowed. Thus, an inline function is one that is allowed to be defined in multiple translation units without violating one definition rule. Okay, inline functions have two primary requirements. The compiler needs to be able to see the full definition of an inline function in each translation unit where the function is used. The definition can occur after the point of use if a forward declaration is also provided. Every definition for an inline function with external linkage must be identical, otherwise undefined behavior will result. Okay, point 1 and 2 are confusing. The compiler needs to be able to see the full definition of an inline function in each translation unit where the function is used. Okay, I understand point 1. The definition can occur after the use, if after the point of use, if a forward declaration is also provided. The compiler will likely not be able to perform inline expansion until it has seen the definition. I need some examples. So main.cpp inline double pi, math.cpp also has inline. Okay, let's do that here. So inline integer max, and then exact same definition over here. Now what about it? The linker will do duplicate them. So without the inline, the linker will complain that they have multiple definition, but with inline, I think the linker will allow it. Yes, that makes sense. Also, the linker and the compiler are assuming that the definitions are equal, right? Yeah, 5, 50. 5 and 50. Inline functions are typically defined in the header file where they can be included into the top of any code file that needs to see the full definition of the identifier. Okay, so inline double. So in their project, main.cpp has pi.h, which defines inline pi. Math.cpp, which is not related to main, but in the same project, also has this include. Oh, wait, I get it. So when this expands, main.cpp will have inline pi, and when this expands, math.cpp will also have an inline pi. So same definition, and the linker won't complain. This is particularly useful for header-only libraries. Wait, hold on. So if I have global stuff, and then I do inline, then I delete this. This is including global stuff, and let's say this includes global stuff. Wait, what's the issue? Whoops. Let's take this. Wouldn't every function in the header file need to be defined as inline? So max for 5. And then let's say a max 10, 9. Show max 10, 9. Why is it this not syntax highlighted? Oh, now it is. So this will expand, right? And this definition of max will go here. The definition of max will also go here. And the linker won't cause a problem. This is particularly useful for header-only libraries. Okay. Avoid the use of the inline keyword unless you have a specific compelling reason to do so. Okay, so 550, it's not causing an error. If I remove the inline, it should cause an error, right? Yeah. Linker error, one or more multiply define symbol found. So why not make all functions inline and defined in the header file? Because doing so can increase your compile time significantly. When a header containing an inline function is included into a source file, that function definition will be compiled as part of that translation unit. An inline function included into 6 translation unit will have its definition compiled 6 times. Conversely, a function defined in a source file will have its definition compiled only once. Okay, so what they're saying is, if max was here, you would have one translation unit with max defined, another translation unit with no max. But because we have uh, we are putting max in global stuff, we have max in 2 places, so the compiler will have to compile max here and compile max here as well. So it increases compile time. But if we have max.cpp, we only need to compile max.cpp and the linker will just link them. Second, if a function defined in a source file changes, only that single source file needs to be recompiled. When an inline function in a header file changes, every code that includes that header needs to be recompiled. Okay. Inline variables. C++17 introduces inline variables, which are variables that are allowed to be defined in multiple files. Inline variables work similarly to inline functions and have the same requirement. The compiler must be able to see an identical full definition everywhere the variable is used. I was confused last time, but I guess this makes sense. Sharing global constants across multiple files. Global constants as internal variables. Prior to C++17, the following is the easiest and the most common solution. You mean static variables, right? Variables in one translation unit. Create a header file to hold these constants. Inside these header files, define a namespace. Add all your constant inside that namespace. Include the header file wherever you need it. So constants.h, but define all the constant in the constant namespace. And then whenever some CPP file needs to use, for example, my gravity, it will just include this header file like they did here. So constants.py. But I think the problem here is that if they do include, the entire thing gets included, even the ones they won't use. So for example, Avogadro's number, they won't use it, but it's still included. While this is simple, every time constant.h gets included into a different code file, each of these variables is copied into the including code file. Therefore, if constants.h gets included into 20 different code files, each of these variables is duplicated 20 times. Header guards won't stop this from happening. Okay. Changing a single constant value would require recompiling every file that includes the constant header. If the constants are large and can't be optimized away, this can use a lot of memory. So the advantage is it works prior to C++17. Global constants as external variable. If you're actively changing values or adding new constants, the prior solution might be problematic. One way to avoid these problems is by turning these constants into external variable. External constant, external constant, external constant. Since we can then have a single variable initialized once that is shared across all files. Wait a minute. Oh, in constants.cpp, in constants.h, they declared it, but they did not define it. Since the actual variables are inside a namespace, the forward declarations need to be inside a namespace as well. Okay. So they declared it using the extern keyword. In constants.cpp, they defined it. So you just need to link constants.cpp, right? You don't need to. The constants.cpp will need to compile once and then not again, right? Use in the code file stays the same. Or there, including h.h. Oh, so now if I change any value over here, this gets recompiled. Otherwise, before, I think both of them had to be recompiled. I think. Yeah, actually, yeah. Because then both of them would be in one translation unit. This time, they're in two separate translation units. Now the symbolic constants will get instantiated only once in constants.cpp instead of in each code file where constant.h is included. And all uses of these constants will be linked to a version instantiated in constants.cpp. Any changes made to constant.cpp will require recompiling only constants.cpp. Oh, I see. So now this main in constant.h is one translation unit, and then constant.cpp and constant.h is a separate translation unit. However, there are a couple of downsides to this method. First, because only the variable's definition are constant expression, these constants, wait, hold on. These constants are constant expressions only within the file they are defined in. In other files, the compiler will only see the forward declaration, which doesn't define a constant expression value, and it must be resolved by the linker. This means outside of the file where they define, these variables can't be used in a constant expression. Second, because constant expressions are typically optimized more than runtime expressions, the compiler may not be able to optimize these as much. Given the downsides, prefer defining your constants in a header file if you find that values of your constants are changing a lot, and this is leading to long compilation times. we can temporarily move just the appending constants into a .cpp file. So this also works prior to C++17. Global constants are inline variables. In lesson 7.9, we covered inline variables, which are variables that can have more than one definition, as long as those definitions are identical. By making our constant expression variables inline, we can define them in a header file and then include them in any .cpp file that requires them. This avoids both the one definition rule and the downside of duplicated variables. So example, you have inline, main.cpp. And if you have some other .cpp that also includes this, they will be in a separate translation unit. Okay. So this is one way to share global constants, which is also constant expression. So advantages can be used in constant expression in any translation unit. Only one copy of each variable is required. Only works in C++17 onwards. Changing anything in the header file requires recompiling files including the header. Oh yeah, I didn't think of that. Because constants.h and main.cpp together form one translation unit. And if you have another .cpp that uses this, they would form a separate translation unit. So it's a double compilation. If you need to use global constant, then you compiler C++17 capable before defining inline constant expression global variables in a header file. Static local variables. Okay, I think static local variables, I might have said this before. Basically, it's this. It's the values defined within the curly brackets. Like this. The ones that get introduced within the local scope, and then they get deleted right after the scope ends. Static has different meanings in different contexts. Well, before we use static to mean within one translation unit, like static, this function over here is in one translation unit. But static inside the curly brackets means it's defined. Well, it actually means the same thing. It's defined within the entire translation unit. So hold on. If I do increment void std cout a new line int a 0, and then I will do a plus equal 1. I will call increment many times, and then static means it's defined in the entire translation unit. So basically what's going to happen, because it's this makes the scope outside of the curly bracket. Yeah. That means a is initialized to 0 at first. Wait, no, I think I'm wrong. Is the definition within the, what's the scope of this? So anyways, a is initialized to 0 first, and then it becomes 1. But over here, a becomes 1, and then a becomes 2. So basically, the previous definition, the previous value of a still retains. So a does not get deleted. Static a does not get deleted. The value is remembered. So first it's 1, it becomes 1, and then if you run increment again, the previous value was 1, and then it becomes 2. And then if you run increment again, it becomes 3. So if I run this, but I don't know if it's correct to say that the scope of A is within the entire translation unit. So a.cpp main.cpp show max unreferenced function with internal linkage. It's treated as a warning. Local variable. Okay, this is initialized but not referenced. This has unreferenced function with internal linkage. I don't think they will allow this. No, let's try. A.cpp and then will it compile? Is this compile? This is compiling, right? Okay, it worked. Five. Okay, see, 1, 2, 3, 4, 5, 6. So the value of A is retained, like the value of A is remembered from the previous call. Using the static keyword on a local variable changes its duration from automatic duration to static duration. This means the variable is now created at the start of the program and destroyed at the end of the program, just like global variables. As a result, the static variable will retain its value even after it goes out of scope. Okay. We can use this for ID generation because during runtime, if you keep incrementing, there'll be a different value. Static local variables can be made constant or constant expression. One good use of constant static local variable is when you have a function that needs to use a constant value, but creating or initializing the object is expensive. Okay. If you used a normal local variable, the variable would be created and initialized every time the function was executed. With constant static local variable, you can create and initialize the expensive object once and then reuse it whenever the function is called. Okay, I need an example for this. So don't use static local variables to alter flow. So first call true, and then when they call again, it would be first call would be false. So it would say enter an integer and then enter another integer. But the thing is, if you call get integer again, then it would say enter an integer. If someone reads the code in main without reading the implementation of get integer, they would have no reason to assume that the two calls of get integer do something different. We might try to use get integer to read in the next two integers like we did for addition. But this won't do as we want, as the output is addition, then subtraction. Okay, so the boolean is like they're using a global boolean and then they're passing it as an argument. It's clearer what the argument represents here. Okay, best practice, constant static local variables are generally okay to use. Non-constant static local variable should generally be avoided. If you do use them, ensure the variable never needs to be reset and isn't used to alter program flow. Okay, this is the summary of what we have learned so far. Local scope, this is for local variables. So like that value and then this function parameter, where did it go? This is local, this is local. And then global scope, we saw that. Global scope, this function is global scope. And then those variables for global scope. Automatic duration are created at the point of definition O. So that's with x and y over here. Whenever you call this function, x and y are defined and then they get deleted right after the function ends, right after whatever value is returned. And then static duration is like is the same as the duration of the global variables, where they start at the end of the file and then end after main ends. Variables with static duration are created when the program begins and destroyed when the program ends. Variables with dynamic duration. Okay, I don't think we have done this yet. Linkage summary. Identifier with low linkage means another declaration of the same identifier refers to a unique entity. Okay, this is for local variables. Internal linkage means a declaration of the same identifier within the same translation unit refers to the same object. And then external linkage means that a declaration of the same identifier within the entire program refers to the same object. So internal linkage, static, global variables, static functions. Const global variables are by default internal. And then unnamed namespaces. For external linkage, you have non-static function, non-constant global variables, uh, extern constant global variables, and inline constant global variables, and also namespaces. Words like static and extern are called storage class specifiers. Okay, next chapter. Using declaration and using directives. Oh, I see. I remember this. So we can basically use using namespace std, and then we wouldn't have to call std twice. We can also do cin value. Let's do int value local variable, and let's do cout enter integer. So we can use these functions without calling std, and we can do using namespace std at a global level, so we won't have to use it here either. This is called using declaration, I think. Wait, it's either called using declaration or using directives. I think it's called using declaration. Wait, I'll just see it later. It says failed. Whoops. We need to insert it, extract it. So we can do using namespace std, and we can also use another thing. I'll just show you. Okay, so enter integer 5 and then program ends. We can also do, if you want to be, if you do using namespace std, it's referring to like this shortcut happens with all functions that are defined in namespace std. But if you only want this to happen with one specific function, you just do using std cout, right? And then we have to use std over here. So now this only have, we don't need to use namespace here. We did using std cout. Now we have to use std in every other function that uses standard library. Yeah, works as expected. So also, although the book here says it's a bad practice, back before C++ had support for namespaces, all the names that are now in std namespace were in global namespace. This caused naming collisions between program identifiers and standard library identifiers. Programs that worked under one version of C++ might have a naming conflict with a newer version of C++. In 1995, namespaces were standardized and all the functionality from the standard library were moved out of the global namespace into namespace std. This change broke older code that was still using names without std: As anyone who has worked on a large code base knows, any change to a date code base risks breaking the program. Updating every name that was now moved into std namespace was a massive risk. So doing this using std namespace, using namespace std was a way to get around that. Typing std before everything you use from the standard library can become repetitive, and in some cases can make your code harder to read. C++ provides some solution to both of these problems in the form of using statements. But they do say that this tip is out of date. Your textbooks or tutorial are probably out of date. A qualified name is a name that includes an associated scope. Most often, names are qualified with a namespace using a scope resolution operator. So like this. An unqualified name is a name that does not include a scoping qualifier. Okay, so this is called using declaration. The other one I did was called using directive. A using declaration allows us to use an unqualified name as an alias for a qualified name. So using std cout, that's the compiler, that cout should resolve to std cout. Using directive, now they're using namespace std. This tells the compiler all of the names as std namespace should be accessible without qualification in the current scope. So the problems are using directives allow unqualified access to all of the names from a namespace, potentially including lots of names you will never use. Using directives do not prefer names from the namespace identified by the using directive over other names. Okay, I need some clarification for this one. Using directive do not prefer names from the namespace identified by the using directive over other names. Wait, hold on. So if it's A, B using namespace A, using namespace B, and they do X, the above example, the compiler is unable to determine whether X in main refers to AX or BX. In this case, it will fail to compile with an ambiguous symbol error. Oh, I see. So that's why they discourage it. Even if a using directive do not cause naming collisions today, it makes your code more vulnerable to future collisions. They did namespace foo where they defined A. Using namespace foo, they defined A. Now let's say you update your foo-lib to a new version and foo-lib.h changes to this. What is this? This is foo-lib.h. Okay, we start with foo-lib.h and main.cpp. And then now let's say you update foo-lib to a newer version. Your main.cpp hasn't changed, but it will no longer compile. This is because our using directive causes foo print to be accessible as just print. Oh, it gets confused with this. But that's why they discourage it. There is a more insidious version of this problem that can occur as well. The updated library may introduce a function that not only has the same name but is actually a better match for some function call. In such a case, the compiler may decide to prefer the new function instead. So foo-lib.h, we have int a, and then main.cpp using name foo. We have a, third party library. This program runs and prints 1. Now let's say we update foo-lib library, which includes an updated foo-lib.h. New function added. Oh, so in main.cpp, you have int get long, and then the new foo-lib has int get int. Oh, foo-lib is a third party that introduced this function, but the compiler is going to prefer this one over this one. So now if the user does get.0, it calls get from foo-lib and not from main, and the user wouldn't even know about it. I see. The lack of explicit scope prefixes make it harder for a reader to tell what functions are part of a library and what's part of your program. Okay, that makes sense. The scope of using statements. If a using declaration or using directive is used within the block, the names are applicable to just that block. Okay. So I did using std cout over here. If I do it at a global level, then I can do just cout over here instead of std cout. Do not use using statements in header files or before and include directive. Oh, I see what the issue can be. Global stuff.h might be using std.cout or some std namespace. But if I do using namespace std, like that, then this will also apply to this. Like after the preprocessor opens this up, this std thing will also apply over here. That will cause issues. And also canceling or replacing using statements. There's no way to cancel the using namespace foo here. Once they use the using directive, there's no way anyone can do anything about it. Unnamed and inline namespaces. Unnamed namespaces like this one. This is I think it's global. All content declared in an unnamed namespace is treated as if it is part of the parent namespace. So even though function do something is defined in the unnamed namespace, the function itself is accessible from the parent namespace. In this case, it's the global namespace. This might make unnamed namespaces seem useless, but the other effect of unnamed namespaces is that all identifiers inside unnamed namespaces are treated as if they have an internal linkage. So, okay, over here, they're doing static void to something. And without the, wait, hold on. This has external linkage, right? And now it has internal linkage. It can only be used within this translation unit. But instead of doing this, I can do this unnamed namespace. Yeah. So what this will do, this will put everything inside over here. Like that, 11, 19. Right. So everything inside here is now static. It's now internal linkage. So I don't have to specify static every time. Unnamed namespaces are typically used when you have a lot of content you want to ensure stays local to a given translation unit. Avoid unnamed namespaces in header files. What is this? Okay, so now they're talking about versioning. Let's say you're not happy with do something and you want to improve it in some way that changes how it behaves. If you do this, you risk breaking existing programs using the older version. How do you handle this? One way to create a new version of the function with a different name, but over the course of many changes, you could end up with a whole set of almost identically named functions. Do something v2, do something v3. An alternative is to use an inline namespace. An inline namespace is a namespace that is typically used to version control. Much like an unnamed namespace, anything declared inside an inline namespace is considered part of the parent namespace. Wait, hold on. Okay, however, unlike unnamed namespaces, inline namespaces don't affect linkage. Oh, so they're external, right? Is that what they're saying? To define an inline namespace, we use an inline keyword. So this do something. So the functions in here become part with the parent. Wait. V1, V2, and then if I do inline, they become part with the global scope. So if I do like, if I run a function that, hold on. If I run a function that uses one of these, let's say void my func, and then std cout show max 119. Yeah, let's just say it's this new line. So this will refer to version 1, and if I wanted to refer to version 2 instead, I can do this. Now this is in a global space, and this is in a namespace space, namespace book. Oh. So do something called the inline version of do something, which is v1. Oh, I forgot. Inline allows multiple definition. Like normally, inline allows multiple definitions, so we can define it in header in multiple translation units. In the above calls, callers do something when you get version 1, or do something callers who want to use the newer version can explicitly call version 2 do something. Okay, mixing inline and unnamed namespaces. Whoops. A namespace can be both inline and unnamed, but wouldn't this be useless? However, in such cases, it's probably better to nest an anonymous namespace inside an inline namespace. What? This has the same effect, but still gives you an explicit namespace name you can use. Nest. Okay. Okay, I will just read the summary and quiz. I will just look through it and then I'll in the stream here. Static duration, identifiers, linkage, qualifiers name. The inline keyword has two primary requirements. The compiler needs to be able to see the full definition, and every definition should be identical. Otherwise, undefined behavior will result. Inline functions and variables are particularly useful for header-only libraries. Also, I saw this. Wait, I don't think I saw this before. So enter a positive number. If it's less than 0, a negative number entered, making positive. I think I saw this before. So the mistake here is that in the if statement, they forgot the curly bracket. Yeah. Write a file name constants that make the following program run. If your compiler is C++17 capable, use an inline constant expression variable. Otherwise, use a normal constant expression variable. Max class size should have 35. So we only need to define max class size in constant.h, right? And then it would be inline constant expression, right? Yeah, and then it's within the namespace. I forgot that. Write a function integer accumulate. This would have a static variable. Yep, and this would keep increasing. Okay, I guess I will end the stream here. Uh, I might stream tomorrow or day after tomorrow, depending on my mood. But yeah, see you guys next time, I guess.